Everybody, this is Argon Quantum tutorial. Today, speaker Ruslan Radurin is going to talk about how to solve combinatorial optimization problems on quantum computers. Ruslan is an Argon scholar. He won fellowship, prestigious director's fellowship at Argon. Go ahead, Ruslan.
Thank you, Yuri, for the introduction. Okay, my name is Ruslan. I'm going to talk today about mostly about quantum optimization algorithm, but also I think some more general points about solving optimization problems in quantum computers will come up. The first part of my talk, I'm going to give you some theoretical background, and that would be about an hour. And in the second part, we're going to do a hands-on using Qiskit. I will show you how to implement QAOA and show you some of the practical pitfalls associated with running QAOA. At any point through the presentation, feel free to put your questions in the chat. I think Kathy is monitoring the chat, or Yuri, or maybe both, and I will try to keep an eye myself too. So if there's a question in the chat, I will try to address it as soon as I see it. With that, let me start by saying a few words about some big picture considerations that are relevant here. So when we're thinking about solving problems, optimization problems in particular, what we're usually interested in is the asymptotic complexity of solving this problem. So specifically what this means is we're interested in how the resource requirements, what time requirements or memory requirements grow with the problem size. And this is what those famous classes of problems are referring to, like P, which is class of problems solvable in polynomial time, NP, class of problems where the proof can be verified in polynomial time, and P space, where the problem can be solved in polynomial space but unlimited time. And these are the famous classical complexity classes. In the quantum space, the complexity class we're most interested in is the BQP, bounded error quantum polynomial time, which roughly corresponds to polynomial depth quantum circuits. And this class contains problems that are solvable on quantum computer in polynomial time with an error probability of at most 1/3 for all instances. And it's roughly equal to BPP, bounded error, bounded probability polynomial time. Now, what is the relationship between these classes? Well, so the big one is the P space. So if you can solve something in polynomial time, you're necessarily solving it in polynomial space. So everything is contained in P space. And then, of course, if you can verify the proof in polynomial time, then you can solve the problem in polynomial time as well. So, if you can solve the problem in polynomial time, then you can verify the proof in polynomial time. So P is contained in NP, and of course, P is contained in BQP as well. Now the question is, what is the relationship between NP and BQP? And so, for example, I'll give you an example of problems that are lying in each of these regions of this Venn diagram. If you're thinking about something like finding a shortest path between two nodes in a graph, that's a polynomial time problem, and it's in P. Then the famous example of integer factorization, which is in BQP because there exists a polynomial time quantum algorithm, Shor's algorithm for this problem, yet it's not known to be in P. That is, there is no known classical polynomial time algorithm. And one of the problems that we're going to talk about today is the maximum cut problem is in general NP complete. That is, it's as hard as any problem in NP. However, it is NP complete in the worst case. And on specific instances, like if you're solving maximum cut problem on a simple graph, like a cycle graph, this problem is actually trivial. It's in P. And the reason I kind of bring up this taxonomy is that when talking about how quantum computers can speed up solving optimization problems, we have to be very careful about what we mean by that. Because worst case instances are not always trivial to construct. So saying that maximum cut is NP complete, it's not trivial to saturate that bound. And maybe not all practical problems are like that. Not all practically interesting instances are like that. And proving asymptotic performance, especially of quantum algorithms, is notoriously difficult. So this is something to keep in mind here. And really, the main takeaway is that we are not going to solve NP-complete problems in polynomial time today, or probably ever. It is sort of a folk, a common assumption people hold that that NP is not in BQP. So there are some problems here that are not solvable on quantum computers in polynomial time. Okay, so we're not going to solve NP-complete problems in polynomial time. So what are we doing here? Well, we're going to look at things slightly differently today. And the way we're going to think about solving optimization problems is we're going to think about two kinds of algorithms. So on the left are algorithms with proven performance. So for example, Dijkstra's algorithm of shortest path is a polynomial time algorithm that is always guaranteed to give you a solution. That is the shortest path between two nodes in something like O of V plus E. And in quantum case, there are also algorithms like that, algorithms that are guaranteed to give you a solution of given quality, often exactly correct solution, within certain running time. Like Shor's algorithm is only going to give you integer factors of your integer in some polynomial time. However, the most powerful algorithms, including the most powerful optimization algorithms, both in classical, especially in the classical case, are often heuristic methods. And what I mean by heuristic here is that there is no guarantee of getting the optimal solution, of getting a solution of given quality in the worst case. In the worst case, you either can have no promise about the quality of the solution, or you can have no promise about the running time of the algorithm. And the famous example is using gradient descents for problems that you cannot prove to be convex. That's a heuristic because gradient descent will only work provably for convex problems. And if you have a weird non-convex landscape, or you cannot show that it's convex, then it's a heuristic because you cannot guarantee its success. And we think what I'm going to argue today is that the quantum heuristic algorithms, such as the quantum approximate optimization algorithm that I'll be talking about today, are the most promising algorithms for optimization in the near term. And it's especially promising because the quantum hardware, such as the noisy intermediate scale quantum hardware that becomes available today, provides a unique opportunity to benchmark these heuristic methods and actually answer the questions about their performance. I see there's a question in the chat from Ish. I'm going to read it out and I'm going to answer it. So Ish is asking about the VQE, which is an algorithm that was discussed yesterday, involves a lot of optimization loops, that is outer loop parameter optimization. How do we then classify in terms of BQP when we don't know how many iterations are required? So this is exactly what I'm getting at. The VQE here is a heuristic algorithm, at least the way it is discussed today. That is, we don't know how many outer loop iterations you would require, right? So you cannot say that it will be, for example, at most polynomial time. That is not a polynomial number of iterations in scaling with the problem size. And because you don't have this guarantee, it can be exponential. And in fact, there is a result showing that parameter optimization, even for QAOA, is NP-complete, NP-hard, is hard in short, even for problems that are classically easy. So the parameter optimization problem can be more difficult than their underlying problem. So we do not classify these algorithms in this sense. I mean, they're all, I guess, p-space, right? But they are heuristics, so they're on the right side of this bucket. All this answers Isha's question. And any other questions at this point would be a good time for questions because we're at the end of the first part. So the first part of my talk now is I'm going to talk about how to take a classical optimization problem and map it onto the quantum computer. And I'm going to talk about the maximum cuts problem specifically because it's this commonly used kind of paradigmatic example for quantum optimization. And you'll see a lot of papers that discuss maximum cut. But I will also talk later about the general rules for building quantum Hamiltonians representing arbitrary Boolean functions that you can map any optimization problems you would like onto a quantum computer, as long as it's defined on the Boolean cube. In the maximum cut problem, the goal of maximum cut problem is to split the set of vertices of a graph into two disjoint sets such that you cut as many edges as possible. So for example, if we're looking at this graph on the right, there are 4 nodes in this graph, 2, 3, 4. There are 5 edges in this graph. And if we let the color denote part, so we partition the set of vertices into green ones and red ones, then we cut the 4 edges between these vertices. We can write it out as an optimization problem in the following way. So we're summing of all edges, 1 minus Si Sj, where Si and Sj is -1 and +1, denoting the part assignment of the vertices. So here we're saying that all green vertices are assigned label -1, and all red vertices are assigned the label +1. To verify that it's correct, if you look at this term, so this contribution of each edge to the cut. So if both variables have labels that have the same sign, then this becomes 0, so there's no contribution to the cut. And if 2 vertices have different sign, then this SISJ becomes -1, so the whole thing becomes 1, and so the cut is increased by 1. So this is a correct formulation for maximum cut problem. Okay, so we're starting with this classical optimization problem on the left. We're trying to find some configuration S, binary configuration S, that maximizes our objective function. And this is all of the problems we're going to consider today are going to have form like that. And what we want to do is we want to solve them somehow on a quantum computer. So on a high level, what we do is, and this is not the only way to do it, but this is the way of doing it that I'm going to talk about today. We're going to take this optimization problem, classic optimization problem, and we're going to convert it into a problem of characterizing some Hamiltonian. And then the spectrum of that Hamiltonian will encode the problem, the objective function. And then the ground state of this Hamiltonian, the highest energy eigenstate of this Hamiltonian, would encode the maximum configuration, the configuration that maximizes the objective function. Let me quickly unpack this. So we're going to take our objective function and we're going to construct some Hamiltonian, which is Hermitian operator, Hermitian matrix, that encodes this objective function in its spectrum, in its eigenvalues. And then our solution, which in classical case, some configuration, which is a string of -1 and +1s of length n, where n is the number of variables. In quantum case, this will become encoded in the highest energy eigenstate, or in more linear algebra terms, largest eigenvalue eigenvector of this operator. And the observable associated with the corresponding to the value of the objective function in a given configuration is the energy of the Hamiltonian with the given quantum state. Now, the nice thing about this is that because our Hamiltonian is classical, that is, it's a diagonal operator, this eigenstate, this highest value energy eigenstate, will be a computational basis state. So if we measure it, we will get the solution to our problem with probability 1. So there is, in ideal setting where we solve the problem exactly, there is no randomness to it. Okay, so what does this Hamiltonian actually look like? So what we want is a Hamiltonian that acts on a computational basis state x as f of x. And so what it looks like is it's a matrix of 2 to the power of n by 2 to the power of n that has on its diagonal all values of the objective function on all possible binary strings. And then it is easy to check that if it acts on, for example, 0, 0, 0, which is represented by a vector which has 1 in the first entry and zeros elsewhere, then the action of this operator on this vector will be exactly f of all zeros. And the same is true in the general case. So that is, if we look at the action of this operator on an arbitrary computational basis state, which is encoded by a vector which has 1 in the entry corresponding to this binary string and zeros elsewhere, then the action for Hamiltonian will be exactly f of x. That is, it will add a phase of f of x. Now, this matrix that I wrote is too large. It's 2 to the power of n by 2 to the power of n. So it's too large to construct explicitly. And in fact, if we were to construct it explicitly, we would have already found the solution of our optimization problem, because you can just look at the diagonal of this operator and pick the smallest value. So it would be a little silly. So the question is, how do you construct this Hamiltonian efficiently? And the way we're going to do this is we're going to build it from PauliZ matrices. But first, let's quickly recap the notation we're going to be using. I think it's the same notation that's used by other speakers the last 2 days, but it's always good to make sure we're all on the same page. So when I write cat x, this is the same as in classical case, bold x or x with an arrow over it. It's just a notation for a column vector. And when I write bra y, this is conjugate transpose of cat y. And it's a row vector with elements being conjugate transposed of the y column vector. This simply denotes, this bra y cat x simply denotes inner product between y and x. And cat x bra y, this denotes outer product between x and y. And this, I think, is all the notation we're going to use today. Let's go back to our maxcat objective. And so what I'm going to do is I'm going to show you that we can just take these variables s that are plus or minus 1, and we can construct the Hamiltonian by simply mapping these binary variables si onto the eigenvalues of z, of PauliZ matrix. And what this would mean is that all we do is we mechanically take the formula and we replace each si with a PauliZ operator acting on the corresponding qubit. PauliZ acting on the ith qubit. And this is what we're going to do. And next, what I'm going to show you is that this is indeed correct. And I'm just kind of walk you through what's going on here to give you a sense of why this is indeed correct. So what we want to show that this is correct is we want to show that that this operator acts on the computational basis state x as d of x, as the value of the objective function on that binary string. So let's show that. So the PauliZ operator is this matrix. It's diagonal matrix with 1 and minus 1. It's diagonal. And it's easy to see that it has eigenvalues minus 1 and plus 1 with eigenvectors being computational basis state. So you can apply it to vector 0, to cat 0, which is computational basis state 0, and it's simply a vector of 1, 0, and of course it stays 0. And if you have computational basis state 1, which is 0, 1 vector, then the action of PauliZ matrix on this vector gives you minus 1 phase. So in short, the action of PauliZ operator on the computational basis state x is adding a phase of minus 1 to the power of x, where x is either 0 or 1. Now, if we have PauliZ acting on ith qubit, what we mean by that is that we have a operator that is acting on all n qubits, but its identity everywhere else. Its identity tensor product of identities on both ends, and then z acting on the ith qubit. And here I'm making an assumption that z is somewhere in the middle. So in general, if z is like the 0th qubit, there's no identities on the left, for example. But for simplicity of notation, I'm just going to assume. And then the action of this operator on ith qubit is easy to see. It's going to add a phase of -1 to the power of xi, where xi is ith entry of the binary string corresponding to this computational basis. Furthermore, if we have two PauliZs, zi and zj, then the action of this operator, which is a product of two PauliZs, is -1 to the power of xi, -1 to the power of xj. That is adding a phase of -1 to the power of xi, -1 to the power of xj. And here, once again, I'm just assuming for the sake of notation that we reordered qubits such that they are adjacent. Okay. So this is the action of ZZ operator. Now let me show you that this is the right action. And so what we're going to do is we're going to take our objective, our max-cut objective, and we're going to take it from SI being -1 and +1 to XI being 0, 1, which is a trivial switch. We can just say SI equals -1 to the power of XI. And this should already start looking familiar. So our new reformulated objective now is each contribution of each edge is 1 minus power 1 to the power of xi, -1 to the power of xj. So remember, what we want to show is that in our max-cut Hamiltonian, it acts on the computational basis state x as t of x, as the value of the objective function on the corresponding binary string. And from what you've seen before, it should be clear that it is exactly what it does. Just walk through it. So this is our Hamiltonian acting on some computational basis state x. Then by linearity, we can open these brackets. To the first term, this is just 1. Identity just does 1. And the second term gives us -1 to the power of xi, -1 to the power of xj, which is exactly the value for our objective function. And so this gives us this shows that the Hamiltonian does indeed correctly implement our objective function. So what we've shown is that the Hamiltonian encoding our max-cut objective function can be constructed by simply mapping the binary variables si, -1 and +1 onto the eigenvalues of PauliZ. And note that even though I only walked you through the example of max-cut, the very same procedure will work for any objective that is built by some products of binary variables. They need not be, for example, quadratic. So you can have product of 5 S's, and what would that become is product of 5 PauliZs. Any questions on the construction of the Hamiltonian representing the max-cut objective function? What the size of this operator, the size of this Hamiltonian, is 2 to the power of n by 2 to the power of n, because we write zi, zj, it's a operator acting on n qubits. So it's a 2 to the power of n by 2 to the power of n operator. So we cannot, as I said earlier, we cannot write this out explicitly. How do we do it in general? How do we build this Hamiltonian in general? Or maybe a better question is, why can we build it? Why can we always build it? So, and the method that I'm going to show you is due to this excellent paper by Stuart Hatfield. I highly recommend. So what we want to do now is we want to construct a Hamiltonian that acts on the computational basis state x by adding a phase f of x. So first, let me give you a quick primer on Boolean analysis of Boolean function. So consider some arbitrary Boolean function. So here, just to show the generality of this, I'm considering a maximum function, which is not even a typical kind of objective function optimization problem. So, and I'm gonna kind of go willy-nilly between x being -1 and +1 and x being 0, 1. And we know that, as I've shown before, we can always do this by doing this change of variables. So this maximum function can be expressed as a multilinear polynomial of this form. Now, how can we construct this multilinear polynomial? Note that any Boolean objective function can be written out as sum of f acting on some configuration times indicator polynomial corresponding to this configuration, which is 0 if x is not equal to a and 1 if x is equal to a. And this indicator polynomial can be constructed explicitly this way. So for example, for our maximum function, by building these indicator polynomials explicitly and adding the computing the corresponding values of the function, we can build the multilinear polynomial representation of this. Now let me quickly add some annotations. I'm going to write x to the power of set s to be a monomial corresponding to s, namely it's a product of xi over indices that are in this set s. And so this multilinear polynomial is actually a Fourier expansion of this Boolean function. And these coefficients are Fourier coefficients corresponding to this Boolean function. And there is a result showing that this multilinear polynomial always exists and is unique. So for a given objective function, we have a unique multilinear polynomial representing it. Okay, now back to our Hamiltonians. So note that constructing this action of the Hamiltonian is actually you can get this action by building a Hamiltonian as a sum of f of x times projector onto the computational basis state x. Right? This holds because this projector will give you 1 if you're projecting if x is itself, is x, if you're projecting x onto x, and it will give you 0 if you're projecting some eigenstate, some computational basis state that is not equal to x onto x, because computational basis states are an orthogonal basis. Okay. And just comparing these two, you can already see that this is how you do it. So you go from, in classical case, indicator polynomials to projector operators in the quantum case. And finally, just to and then note that because products of PauliZ implement parity functions, so product of PauliZ acts on the computational basis state x as by adding a phase x to the power of s, then taking the Fourier expansion of your classical Boolean objective function and taking those Fourier coefficients, plugging them into this formula will give you a unique n-qubit Hamiltonian representing f. So, kind of in a short, and the algorithm, the recipe for constructing a Hamiltonian for an arbitrary optimization, arbitrary objective function, is you start by performing Fourier expansion of this function, and then you replace the multilinear, the monomials x to the power of s by products of PauliZ. Now, this is a general recipe in a sense a proof that this representation always exists. But it is in general hard to compute the Fourier expansion. And in practice, you can build this Hamiltonian from simple building blocks. And I would recommend this paper, Stewart's paper, that kind of walks you through how this can be built for common Boolean functions. Finally, in practice, your objective function usually already comes as a polynomial. For example, in maxcut, we already started out with a polynomial. So if it's a polynomial, it's easy to convert to an objective function it's easy to convert to a Hamiltonian by replacing the products of x with products of PauliZ, as I've shown you for maxcut. So now I'm going to talk about solving this problem. So we've converted this classical optimization problem into a form that is convenient to solve on a quantum computer. So how do we actually solve it? How do we find this highest energy eigenstate of this Hamiltonian? And this we're going to do using quantum approximation algorithm, which is a heuristic algorithm for finding or solving conventional optimization problems. And the way it works is it prepares the following parameterized trial state, or which is commonly referred to as ansatz. So we start in the vacuum state, all zeros. We apply Hadamard on each qubit, and then we apply a sequence of alternating operators, where one operator is matrix exponent of minus I times some free parameter gamma times the problem Hamiltonian, and another one is exponent of minus I some free parameter beta, and B is the mixer Hamiltonian. So the problem Hamiltonian is this combination of PauliZ matrices that we just learned to construct, and the B is a mixer Hamiltonian, and it's the commonly used one is sum of Pauli X on all qubits. And then what is typically done is we use some method to find parameters beta gamma that maximize the expected value of the objective function. Now, why do we think it's a good ansatz? So if we have P, so P is the number of these pairs of alternating operators that we apply in sequence. So we know that if we have infinite number of these operators, then this can at least exactly approximate something called the diabatic quantum algorithm, which is guaranteed to find the exact optimal solution in the limit of potentially exponentially large running time. Now for small p, the picture is somewhat mixed, but there are some results indicating the potential for quantum advantage. For example, there are demonstrations that due to a different mechanism, QAOA can outperform, for example, simulate annealing and quantum annealing for certain classes of problems. Now, one thing you may wonder about is how do we implement this in gates? So this is easy, Hadamard is easy, but this may be not obvious to you. And maybe this is something that Dmitry has talked about yesterday, but I'm going to reiterate it anyway. Because this is very similar. This is effectively you're simulating the Hamiltonian C for time gamma. This is simply Hamiltonian evolution circuits. I'm going to assume a pretty standard basis state. You have your PauliZ, your Hadamard, and your RZ gate. I actually don't even need phase gate. Okay, so let's start with a simple operator and work our way to evolving our Hamiltonian. The simple operator we're going to start with is just PauliZ on one qubit. And what I'm going to show you is that what you can see is that exponent of minus I zt, where t is some free parameter, is equal to rotation around z or with the angle 2 times t. And you can see it by just examining the formula for the RZ gate. So RZ gate is exponent of minus I theta z over 2, which is exactly the operation that we want to implement. And so the circuit for implementing this simple operator is rotation around z for times 2t. I see there's a question in the chat. The question is, can the mixer be sum of z? So the start state is all zeros, which is easier to prepare than a superposition state. So the question is, the question is, if I understand correctly, setting the b, the mixer, to also be, for example, sum over all sum of single qubit PauliZs on all qubits. Okay. Well, the issue with that would be that both the mixer and the phase separated Hamiltonian will be diagonal in the computational basis. And so what this means is that no matter what state you start with, if you only have diagonal operators, they do not change the probability amplitudes of your outcome. Therefore, this does not, no matter how you would vary the parameters, you would get the same samples out. So you need something that is non-diagonal. More specifically, you need something that doesn't commute. So C and B should not commute, otherwise you would not have interference. But you can, theoretically, you can plug in, I think, some of PauliZ here, and it would also be non-trivial. So in general, any non-commuting operator here works. Some are better than others. Thank you for the question. Okay, so we figured out how to implement this simple 1 minus IZT, single qubit PauliZ. Now, what happens if we have a two-body term, so product of two PauliZs? So to see the action, recall that Z has eigenvectors 0, 1 with eigenvalues +1 and -1, and recall from your linear algebra class that exponent of matrix A acting on eigenvector V is equal to exponent of the corresponding eigenvalue. And from this, you can simply write out the action of this operator on all computational basis state. So we can, by writing out its action on the computational basis states, on all of the bases, we can see that it adds a phase with the sign depending on the parity. So it adds a phase factor that is something like -1 to the power of A XOR B. And the circuit implementing that is C0 RZ C0. And you can see this simply by seeing what it does on some input AB. So C0 sets the second register to be A XOR B. And then RZ, by definition, adds the phase equal to the value of this register. And now we add a second C0 to reset the state of the second register back. And so this gate adds a global phase, adds a phase that is equal to the desired phase. So this is the correct circuit to implement exponent of minus I ZZT. And that gives us the two-body terms. And now the last thing we want to have many ZZ terms in our Hamiltonian, our max-cut Hamiltonian. But because they commute, we can just represent them as products of corresponding terms. So if we have sum of two terms in our exponent and they commute, this is simply product of their exponents, meaning we can just concatenate the corresponding circuits. And this is sufficient to build circuit to simulate our max-cut Hamiltonian. that is our problem Hamiltonian. And this is half of our circuit. So this is all of these terms. Now the second part of our circuit is the mixer Hamiltonian, which is exponent of minus I beta sum over all qubits Pauli x. So each of these terms, exponent of minus I xt, can be simulated by noticing that if you sandwich an exponent of minus I zt between two Hadamards, it is equal to the exponent of minus I xt. This is simply because z Hadamard is equal to x. And by just looking at power expansion, you can see that this is indeed the case. And so what that means is to simulate exponent of minus I xt, all we do is we apply Hadamard or z Hadamard. And this gives us a circuit to simulate the entire QAOA ansatz. Okay, so we can compile the QAOA ansatz into gates. Now, finally, let me say a few words about kind of the intuition you may have for this method. So you can think of the initial state, the uniform superposition, as some vector into the power of n-dimensional Hilbert space. And we have our target state, which is the highest energy eigenstate, for example, a maximization problem, as some other vector. And what we are doing is with our trial state, at each point we plug in some parameters and get some different vector. We're trying to vary the parameters beta, gamma to bring this trial state as close as possible to the target state, which may look to some of you familiar and resembling Grover's algorithm, which in a sense it is. It's similar idea of sort of you add a phase factor and then you do something to cancel out the phases. Where the phase factor corresponding is the exponent of the cost Hamiltonian, and the canceling out the amplitudes is the mixer Hamiltonian. Now, from this picture, hopefully it's clear that the quality of the QAOA solution depends heavily on our ability to find good QAOA parameters. And this is something I'm going to touch on in the hands-on part of the talk. Now let me say a few words about the connection to the adiabatic quantum algorithm, which is something that I think commonly comes up as a question. So, a adiabatic quantum algorithm is a way to find some desired eigenstate of the problem Hamiltonian, for example, a ground state or highest energy eigenstate of the problem Hamiltonian. And it's inspired by the adiabatic approximation theorem, which states roughly that if you start in some eigenstate, such as the ground state of a time-dependent Hamiltonian, and you evolve this Hamiltonian slowly enough, and this potentially means exponentially slowly, then you will remain in the instantaneous eigenstate of the system. So if you start in ground state, you will always remain in the ground state, meaning that if you evolve your system into the problem Hamiltonian, then your final system will be in the ground state of the problem Hamiltonian. And you can read out the solution by simply measuring the system at the end of the evolution. So your state throughout the evolution is given by this Hamiltonian, which is where s of t is some smooth function that varies from 0 at the beginning. So you begin in your simple Hamiltonian, and it ends with 1. So in the end, you're all in the problem Hamiltonian. And so in our max cut case, we are going to write it out. We're going to use our problem Hamiltonian to be the max cut, and our initial Hamiltonian, which is our simple Hamiltonian, is just going to be a sum of Pauli x on all qubits, which has the ground state of uniform superposition state. So how can we simulate this on a quantum computer? And by what I'm going to do is I'm going to show you what the simulation circuit for this is, and I'm going to show you how it can be considered a special case of QAOA. Okay, so let's go to the basics. So we have some quantum state evolution. We start in of time 0, and we assume that our initial state, we start in time t0 equals 0. And we're also going to absorb Planck's constant into H. And so we start in state psi of 0, and we evolve it with some unitary. And so we get our time-dependent final state psi of t. The evolution is described. So if we're evolving with some, right? So if we're evolving with some Hamiltonian H of t, then the evolution is related to the system Hamiltonian by the Schrodinger's equation. And the solution to this simple differential equation is, if our Hamiltonian is time dependent but commutes with itself at different points in time, is you can say simply it's exponent of integral of Hamiltonian over the time period. Now, for a time independent Hamiltonian, this is the solution to this is even simpler. It's just exponent of minus I H t. Now, let's get to this time independent Hamiltonian. So first, if we have some two non-commuting Hamiltonians, A and B, then by Schroeder formula, if you have this product of e to the iat over n, e to the ibt over n to the power of n, and you send n to infinity, then this is equal to the exponent or time evolution of these of the sum of these two Hamiltonians. And as a corollary, you can truncate it to just the first two terms. Now, let's consider our time-dependent Hamiltonian and break down our evolution into small chunks such that it's constant over each chunk. So we're going to set some small delta t, and we're going to break up our time-dependent Hamiltonian such that it's constant over this, such that we can assume that it's constant over this delta t. And this, exactly, so we're going to be assuming that it's approximately constant over this interval. And so our evolution is now product of these time-dependent chunks, where in each chunk the Hamiltonian is approximately constant. They don't commute necessarily, so we apply the Schroeder-Suzuki decomposition, and now we get this product of exponent of I minus S j delta t, and this is because our Hamiltonian is evolving with 1 minus S of t hd plus S hp. And this hopefully resembles the quantum approximate optimization algorithm ansatz. So if you look at, just to put them side by side, on the left we have the QAOA, and our ansatz is product of exponents of minus I beta b minus I gamma c. And on the right, we have the same product, but we have, instead of beta, we have 1 minus S j delta t. And instead of gamma, we have S j delta t. And so by simply setting the parameters appropriately and setting the number of steps p sufficiently high, we can simulate a adiabatic quantum algorithm using QAOA circuits. So this is the connection between the two. This is what I meant when I said in the limit of p approximates in infinity, you can exactly simulate the adiabatic quantum computation. Why the need to discretize time evolution in AQC? Well, fundamentally, fundamentally, the issue is that we in general cannot just exponentiate this Hamiltonian because it has non-commuting terms. So we cannot directly simulate it. So to do that, we have to break it down using this, the Schroeder formula, and then break it down into chunks simulated with small time steps. So if, for example, these two things were commuting, so we only had for example, we didn't have HD was, for example, single qubit PauliZs, then we could just exponentiate it directly. But not in this case. I hope this answers all. Okay. Would the choice of delta T need to be roughly proportional to the spectral gap of H? Is there some way of estimating this quantity without running several trial experiments? This is a good question. I think delta T is the overall running time, I think, scales roughly as 1 over spectral gap squared. So yes to the first question. To the second question, I'm not sure. I think for some problems you can, but this is not something I'm familiar with. And in any case, in QAOA, we don't have to deal with this because in QAOA, we simply let these things be free parameters. So in a sense, we're fixing the number of steps and we're letting delta T be free parameter, and then we somehow optimize them using an outer loop optimizer. Now let me switch gears, and I think this is the last part of my theory presentation.
From Carlin. I don't know, did you answer it already?
Yeah.
Okay.
The question about the delta T, the choice of delta T.
All right, excellent.
Now, as the final part of my talk, I'm going to talk briefly about the challenge of optimizing the QAOA parameters. And as I said before, typically the way it is done, the way those parameters, beta and gamma, which are the time for how long you evolve the system with each Hamiltonian, are chosen, is unlike in adiabatic methods where you do this by leveraging your knowledge about the spectral gap. Here we just use a classical outer loop method to optimize them as a black box. Now, one nice property of QAOA is that the energy, this expected value of the sampled solution, can be evaluated without necessarily using classical quantum computer in some cases. So you can do it purely classically. And then you can, using this, optimize, that is, find optimal QAOA parameters purely classically, and then only run QAOA on a quantum computer to sample the optimal solutions. So to show this, let's look at our QAOA ansatz, and let's just denote by UB the exponent of the mixer, and by UC exponent of the phase separating or post-Hamiltonian. Then writing out QAOA energy for P equals 1 for max cut. So the identity commutes out, and what we're left here is ZZ, sum of over all edges ZZ terms, and on each sides are these UB and UC operators. Then the contribution of each edge is equal to this. And if you go through it, middle out, you can start by noticing that UB, which is product of exponents of I, beta, and then single qubit XM, this will commute through the ZZ term and cancel with itself on the right whenever the qubit the X is acting on is not one of these qubits. So whenever the qubit M is not J or K, we can commute the term through and cancel it out. So the only thing that will be left is the mixer term acting on the qubits that are corresponding to this edge, that are the same qubits on which those PauliZs act. Now, if you have the phase separation operator, it's easy to see the same way, that everything will commute through except the terms that are touching one of these two qubits. So in general, what in this case for P equals 1, the only terms that come into play are terms that are in one neighborhood of Zj, Zk. And so the number of qubits that you need to simulate is only equal to the one neighborhood of Zj, Zk, which can be much smaller than the total number of qubits on the problem. For example, if you have a 3 regular graph, you will have no more than 6 qubits of 6 nodes in your one neighborhood of this term. So even if you have, a million node graph, you can still evaluate the energy of QAOA, and you can still train a parameters purely classically in simulation by leveraging this observation. And if you have higher P, all you do is you keep growing your neighborhood to include everything that is in what is sometimes called the reverse causal cone of this operator. Okay, to sum up what I've talked about today briefly, first, QAOA will not solve NP-complete problems in polynomial. However, it is a promising heuristic for the noisy intermediate scale quantum era, that is the near-term quantum hardware. For any Boolean function on n qubits, we can construct the corresponding Hamiltonian, and therefore we can solve it using QAOA. QAOA has a deep connection to the adiabatic quantum algorithm, which can sometimes be helpful and can sometimes be misleading. And finally, we can often train QAOA parameters purely classically in simulation. And to the question of Alvin, the presentation slides are in GitHub, the same GitHub that was used in the last 2 days. I think it's slides.pdf in the Wednesday folder on GitHub. Okay, and now I'm going to move on to the hands-on part. Thank you, Yuri, for posting the link. Okay, so what we're going to do is we're going to solve max cut problem on a simple graph. So recall that our objective is this. It's sum over edges 1 minus SISJ. And what we're going to do is going to drop some constants, because the only thing that matters to our solution is this part, the objective. And we don't actually care about this identity. So we're going to just reformulate our Hamiltonian as sum over edges minus SISJ. And so this gives us this maximization problem, which, as I've shown you earlier, would map to a Hamiltonian, which is sum over edges minus ZIZJ. You can simply take these binary variables and map them onto the eigenvalues of PauliZ matrix. So if this is our Hamiltonian, then our QAOA circuit is we start in the vacuum state, apply our layer Hadamard's, and then apply a sequence of alternation operators. So what we need to do to run QAOA is we need to implement these two operators. So let's start by importing everything. And we're going to consider this graph. It's a graph on 5 nodes. It's a bipartite graph. I'm going to be solving this. So let's start by building the circuit for the cost operator. So the building blocks are, I have another one. Because this is sum over edges of commuting terms, this can be unrolled into simply a product of exponent of minus I gamma ZIZJ. Therefore, what we need to do is we need to implement ZZ term by itself, and then because they commute, we can concatenate the corresponding circuits. So the code to implement the ZZ term is simply C naught RZ 2 times gamma C naught. And then to implement the entire cost operator circuit, all we do is for each edge, we append the circuit implementing the ZZ term. And this gives us the entire cost operator circuit. And we can check that it indeed produces the correct output. We get C naught RZ C naught for each ZZ term corresponding to each edge. And here I just plugged some random parameter to get some nice output. Okay, secondly, we need to build the mixer operator. And the mixer operator is just 1 of minus I beta x on each qubit. So to implement exponent minus I beta x, this is simply Rx. And then the entire mixer operator circuit is for each qubit, for each node, we append this x term. This gives us the mixer circuit. We can plot it, and it indeed looks correct. It's Rx on each qubit. Okay, and with this, we can build the entire circuit. So we start with just an empty circuit. Then we apply a layer of Hadamards. So we apply Hadamard on each gate, on each qubit. And then we p times apply first the cost operator circuit, which is this. And then we apply the mixer operator circuit, which is this. And in the end, we measure. And this gives us the QAOA circuit. We can draw it. It doesn't quite fit on the screen, but it looks correct. So we first have this layer of Hadamards. Then we apply our mixer operator circuit. And then in the end, we apply our phase separation circuit. Mixer operator circuit. Okay, and now that we have it, we can run it. Now, I'm only going to be talking about running in simulators today, but it's very easy to switch to actual quantum hardware by just changing the backend in Qiskit. But note that even this small example may not run very nicely on a real quantum computer. Now, one thing to note is that Qiskit uses an ordering where the 0th qubit is the rightmost, so the least significant bit in the bit string, which is different from the traditional textbook notation, where your 0 element is the leftmost binary string. So what we have to do is for each sample we've received from Qiskit, we have to invert it. I have a little helper function to do that. Yeah, so we can take our circuit, which we've built earlier, and we can run it simply in simulator. And we get some results out. And it doesn't look like much because they all seem to have roughly the same counts. So this is some binary string, and this is the number of times we've sampled that binary string. So to answer how good were our results, so we can kind of tell here they're not that great. But to answer how good they are exactly, what we need to do is we need to be able to evaluate the value of objective function on these samples. And here is a simple max cut objective that takes the graph G, and all it does is it goes through all the edges of this graph, and it checks if the corresponding bits are equal. And if they're not equal, that means the edge is cut. For example, max cut objective of 00011 is 6. Or -6 because for convention we are minimizing. And now we can compute the energy of our sample, this value, psi c psi. And what we do is we go through our counts, and for each measurement outcome we compute its energy multiplied by the number of times we've obtained that measurement outcome, and then we divide by total number of counts. And this gives us the expected value of the objective function. And we get something that's like 3 point something. Remember that our optimum is 6. So this is not too great. Now, to get better solutions, what we need to do is we need to find the good parameters beta and gamma for QAOA. And so what we're going to do is we're going to simply use SciPy implementation of constraint optimization by linear approximation, which is a simple black box optimizer that builds a linear model in some trust region and uses this to go downhill. And so to use this SciPy minimize method, what we need to do is we need to wrap our objective our QAOA into some black box objective function that compiler can optimize. And so this is a simple function that does that. So it returns some function that takes in parameters theta, interprets the first part of theta to be betas and the second part of theta to be gammas, and then builds the QAOA circuit, and then runs this QAOA circuit and returns the energy. And then a compiler can take this function and can find parameters theta that minimize the energy. And now we can put it all together. So I'm going to set p equals 5, and I'm going to grab the objective, and from some initial point, I'm going to run the SciPy minimize with compiler. I'm going to set number of iterations to 2,500. And so what we get is we get energy of 5.29, which is not too far from optimum. Remember, our optimum is 6. So this is much better than what we had previously, which was something like 3. Okay. Now, this only gave us the optimal parameters. Now what we need to do is we need to get the solution out. And for that, we need to take the circuit and run it with the optimal parameters and get the counts. What we can see here is that the most frequent counts are the counts corresponding to the solution. So our optimal solution is either 00011 or 11100. And those are the two most frequent samples here. So that's good. We frequently get the optimal solution. This is what we want. Now we can look at how good the results are by just plotting how many of samples we get for each energy level. And we see that for optimal solution, which is energy 6, we get, what about like more than 70% of our samples have optimal solution, correspond to the optimal solution. This is pretty good. And we can look at all of our samples and just take the best one by just picking the one that has the lowest energy. And by looking at our graph, we can see that this is indeed the optimal solution. So we cut all the edges in the graph. So that's good. Now, in that example, we estimated the QAOA energy from samples. Now, what happens if we use the entirety of the quantum state to estimate the energy? And for that, we can use Qiskit's state vector simulator, which I think Kevin discussed on Monday. And what state vector simulator gives you is the full quantum state. So for example, if our state is a Bell state, then the state vector will spit out a vector of 1 over square root of 2, 0, 0, 1 over square root of 2. Now, we have to invert the state vector to account for the Qiskit ordering of qubits. And I have some helper function here to do that. Now, I'm going to re-implement the method for building QAOA circuit because we shouldn't measure if we're using state vector. And finally, the last thing we need is we need a method to convert our state vector to the energy estimate. And for this, I'm just going to take state vector and convert it into counts. And now we can put this all together and we can just plug in the parameters that we got previously and run them and see what comes out. Now, let's make sure that our implementation is correct by verifying that the energy is equal. So we take our parameters and we plug in so we plugged in the previously optimized parameters we got out of the state vector, and we're looking at the value of the energy of the state vector, and it is indeed correct. It's the same value as we got from samples. So this is good. We didn't have any bugs. Great question, Alex. So Alex had a question. I understand that all of these tutorial problems have been run in ideal simulators, but just how much does the noise in actual quantum computers affect results such as these? So one thing I can point you to is So here's an example of what noise does to you. So here we're running QAOA circuits for max cut on this 5-qubit device. And we're using these 4 qubits. And we're running it on star graph. So our graph is 4-node star graph that looks like this. So we're solving max cut on this graph, and we're mapping it on the line segment of IBM QAOA. And so here the green line is the noiseless energy. And as you can see, as we increase the QAOA depth P, the noiseless energy approximates optimal. And for P equals 3, we'll solve the problem exactly. We achieve the optimal solution of 3. Now, if we run on hardware and we start increasing the depth from P equals 1 to P equals 2, we get a little bit of improvement in expected value of the objective function, but it's well below noiseless case. But if we go from P equals 2 to P equals 3 here, then our expected value of the objective function actually drops. So this is what noise does to you. So noise effectively imposes an upper limit on the number of QAOA steps that you can do. I hope this answers your question. Thank you for an excellent question. And I would recommend this paper. It shows a method for mitigating these errors by leveraging the structure of the QAOA ansatz. And I can drop this link in the chat. Okay, so now we're using the full state vector, and let's just see what happens if we run the optimization loop with the full state vector. So now our optimizer gets the energy that's computed from the full state. So it's an exact energy as opposed to energy estimated from samples. And if we do that, and it's going to take a little moment because state vector simulator is a little slower than the QASM sampling-based simulator. So we're running it. We're giving the same budget of function evaluations. The only difference is that we have full energy instead of estimated from samples. I'm going to answer the question from Ish while this is running. So Ish is asking, when doing experiments of IBM QAOA, for example, and say we have a graph that is complete, so to simulate the cost operator, the operator corresponding to the cost Hamiltonian, we need C-naughts between all qubits, which of course does not match the hardware connectivity. So how do we implement C-naughts between qubits which cannot be entangled on hardware? This is a great question, Yish. So what we do is we insert swap gates. So for example, for that example that I've shown you, which had 3 edges, so you need only 6 C-naughts in the ideal case. But because we only have this line connectivity, what we have to do is we need to insert a swap. Insert a swap here. So as a result, we get 9 C-naught gates instead of 6. So to run QAOA on which requires entangling qubits that are not directly connected on hardware, we insert swap gates to move the qubits to be next to each other. And in general, this can be done with at most linear cost by using something called swap networks. But coming back, I see that our state vector simulation has finished, and you can see that our objective function is much better. So we got energy of 5.95. To compare it with what we had from samples, it was about 5.3, 5.2. I guess I can print with more digits. Yeah, so we went from 5.29 something, 5.3, to 5.95. And in fact, by running with a full state vector here, we can get arbitrarily close to true optimum. So if Don't try it now because it'll take forever. But we can plug in 10,000 iterations here, and you will get like 5999. And you might wonder, well, why is this happening? Why do I get so much worse energy, so much worse parameters, and so much worse solution when using the estimate of energy from samples as opposed to the full state vector? And the reason is QAOA gets stuck in a low quality point because of the sampling noise. And you can see this by just verifying that parameters are quite different. Now, it's important to point out that this point that QAOA got stuck in is not a local minimum. So if we take this point and run optimizer with a full state vector from that point, it can actually go downhill. And here we're setting the QAOA's initial step size to be very small, so we're in this tiny neighborhood of that point. So this point is not a local minimum. It's simply a fake local minimum that we get stuck in because of the sampling error, the finite sampling error throwing our optimizer up. And this, maybe to the question of, to Alex's question, this is only going to get worse on the hardware, because on the hardware, the error in your objective is even larger. So you really need to think about the stochasticity of your objective when optimizing it. And this makes it difficult to use some of the off-the-shelf deterministic optimizers like QAOA, which have a baked-in assumption that the objective function value is always correct. Okay, so far I kind of walked you through pedagogically what it takes to implement QAOA, so you have a good understanding of it. Now let me show you how you can skip some of these steps using Qiskit. So what we did, to recap, we chose a problem class, maxcut, and a problem instance. This case, it was this 5-node graph. We built the general Hamiltonian for the problem class by sitting down and deriving it. And then we built this Hamiltonian for the problem instance. From the Hamiltonian, we constructed the QAOA circuit, wrapped the QAOA circuit in a black box function, and used a SciPy method to optimize QAOA parameters. And finally, we sampled the solution by running QAOA circuit with optimized parameters. In general, all of these 7 steps can be handled by Qiskit with their high-level declarative interface. But I'm only going to show you today how to use these steps, keep these steps 3 and 4 by using Qiskit's Hamiltonian functions. So what we're going to do, and this is, I just copied this from Qiskit optimization. So this is method implemented in Qiskit. And what it does is it builds a post-Hamiltonian, which is a Pauli operator, right? It's a sum of Paulis, and each Pauli is a product of 2 PauliZs. The notation here might sound unfamiliar, but this is simply similar to stabilizer tableau notation. So you have string encoding the Pauli X's, string encoding the Pauli Z's, and if both X and Z are 1, then this is Y. So this is exactly like the stabilizer tableau notation. And so now what we can do is we can pass a graph to this get cost operator function, and it will spit out our Hamiltonian. And by matching the Hamiltonian to the Hamiltonian that we know to be correct, you can tell that it's indeed the right Hamiltonian. So it has terms corresponding to each edge with the right coefficient, 0.5. Now, we can make sure that the Hamiltonian is correct by simply using an eigensolver, like a classical NumPy eigensolver, to find its lowest eigenvalue eigenvector. And so we get some eigenvectors. Now we have to convert them to the solution of the maxcut problem, which Qiskit provides a function to do. So we take these eigenvectors and we convert them, and we obtain the solution corresponding to this eigenvector using Qiskit, which is indeed the correct solution. So the Hamiltonian we've built in Qiskit is correct. And this is something you can do if you're running QAOA on your own problem, because you can simply build your Hamiltonian the same way and then check it using exact eigensolver. And of course, you can simply build your Hamiltonian as a matrix. So you can know that your Hamiltonian is the sum of ZZ terms, and each of them is Z tensor product identities. And so you can just build this in NumPy and then just add it up. And you can use this operator in Qiskit. Well, actually, first you probably want to test it. So here we take this operator and we get its eigenvalues and eigenvectors. We get the lowest eigenvalue and corresponding eigenvector. And then if we use Qiskit's method to get the corresponding solution, it's indeed correct. So even the Hamiltonian we built in Qiskit is correct. In NumPy. And finally, we can build the QAOA circuit from this Hamiltonian by just using QAOA variational form implemented in Qiskit. And then the same way as before, we can just take this and plug it in by constructing the circuit. So the method is variational form to construct circuit, and you have to plug in some parameters. Measure and run it on Qiskit, and you'll get some counts out. Similarly to how we did with the circuit that we've built ourselves from gates. And by comparing these two circuits, it doesn't fit on my screen, so you'll have to believe me, but it's the same circuit. Yeah, you can, but if I zoom out, I can see it, you can see it. Yes, it's a layer of Hadamard's and then RZs. They are in slightly different order, but you can see that they match. And the only thing we have to rescale the parameters correctly. Actually, we don't. Doesn't have to happen. Yes, and the two circuits match. And in fact, we can check that they produce the same unitary. So what we can do is we can compute the unitary using Qiskit's unitary simulator. We can compute the unitary corresponding to the circuit that we've built from gates by running the circuit through the unitary simulator and grabbing the unitary. And what I'm doing here is I'm removing some errors that come from numerical instability. So I'm throwing away items that are smaller than 10 times the float epsilon. When you do that, you can check that the two unitaries are equal up to the global phase. And note that even if the Hamiltonian that you've built in NumPy, you can use in Qiskit. But it will be slow in general. So probably only recommend for prototyping. And that's all I have for you today. Thank you for listening, and I'm happy to take any questions. I see there's a question from VJ asking what other black box optimization techniques are available. And the answer is there's many ones in SciPy, and there's actually further ones in Qiskit. If we go back here, we can, instead of Kabila, we can use something like yeah. And we'll get some solution as well, but it may be worse. In general, you can go to SciPy minimize. And there's a whole list of methods available there. Drop this in the chat. Another good library to use is NLOpt, which also has implementations of many different methods. And some of these NLOPT implementation in general better. They are usually don't suffer from like weird memory issues or numerical instabilities. So I'll drop this in the chat as well. Yeah, so you can see that we ran it with Nell-Lamida and we actually got a better solution, 5999. So the lesson is try different methods. Some may work better than others.
And thank you very much, Ruslan. It was a very nice presentation and hands-on session, as usual. Okay, I will see everybody tomorrow at 10 o'clock. Okay, bye
Thank you,
everybody.
guys.